Since the dawn of the space age, humanity has faced one unyielding truth: fuel limits destiny. Every spacecraft, every probe, every mission has been bound by the weight of its own fuel tanks. No matter how powerful the rocket, it can only go as far as the propellant it carries will allow. But that age-old limitation may soon end. High above the Earth, a quiet revolution is taking shape. One that could redefine not only how we travel in space, but how we live there. It's called orbital refueling, and SpaceX is at the heart of this transformation. Imagine rockets that don't have to carry all their fuel from the ground. Imagine refueling depots orbiting Earth, spacecraft topping off their tanks before heading to the Moon, Mars, or beyond. Imagine an entire economy operating in the vacuum of space, where resources, not gravity, dictate the limits of exploration. This is not science fiction. It's the next step in the evolution of spaceflight. And if SpaceX succeeds, orbital refueling will not just change how we reach the stars, it will change what it means to belong there. To understand why orbital refueling is revolutionary, we must first face the brutal physics of rocketry. Every launch is a delicate balance between fuel, mass, and payload. Rockets work by throwing mass out their engines at incredible speed, but to throw more mass, they need more fuel. More fuel makes the rocket heavier, requiring even more fuel to lift it. This vicious cycle, known as the tyranny of the rocket equation, has haunted engineers for over a century. Even today's most advanced rockets, like the SpaceX Falcon 9 or Starship, must carry enormous propellant reserves to escape Earth's gravity. By the time they reach orbit, most of that fuel is gone. What remains is barely enough to adjust trajectory, let alone fly to another planet. That's why every deep space mission so far has been carefully rationed, meticulously planned, and profoundly limited. To explore beyond Earth efficiently, we need to break free of the rocket equation. And SpaceX's answer to that problem is to refuel in space. The idea is as elegant as it is bold. Instead of launching a single rocket loaded with all the fuel it needs for a Mars journey, SpaceX will send multiple starships into orbit. One will be the tanker, carrying only propellant. The other will be the mission vehicle, bound for deep space. Once in orbit, the two will rendezvous, connecting nose to nose in a carefully choreographed dance of precision and engineering. Through specialized valves and pumps, the tanker will transfer its liquid methane and liquid oxygen to the mission ship. No gravity, no refueling stations, just two spacecraft drifting silently above Earth, exchanging the lifeblood of propulsion. Once filled, the mission ship will have the energy to go anywhere, to the Moon, to Mars, or perhaps even beyond. The tanker, meanwhile, will return to Earth, land, and be reused, ready to launch again. It is a system that transforms spaceflight from a single-use journey into a reusable ecosystem. Each mission refuels the next. Each launch builds upon the last. It is a leap from exploration to infrastructure, from adventure to economy. For the first time, space becomes a place we can stay. Yet behind this elegant vision lies one of the most complex technical challenges ever attempted: transferring cryogenic propellants, supercooled liquids near absolute zero, in the vacuum of space is far from simple. On Earth, gravity helps fuel flow from tank to tank. In orbit, there is no up or down. Liquids form floating blobs, pressure fluctuates, and even minor thermal shifts can cause catastrophic failure. To succeed, engineers must control temperature, pressure, and flow with incredible precision. The tanks must remain perfectly sealed, insulated from sunlight, vibration, and radiation. The fluid dynamics are unlike anything experienced on Earth. NASA and SpaceX are now collaborating on these experiments through the Cryogenic Fluid Management Program, a series of tests designed to prove the feasibility of transferring liquid methane and oxygen in microgravity. The first demonstrations will take place in low Earth orbit using modified starships, collecting data, refining systems, and pushing the boundaries of what's possible. If these tests succeed, SpaceX will not just refuel a spacecraft. It will prove that fuel can become a renewable resource in orbit. And that will change everything. With orbital refueling, the cost and complexity of deep space missions could drop by orders of magnitude. Instead of launching massive, fully fueled spacecraft, missions could launch lighter, cheaper, and more frequently. A single Starship, refueled in orbit, could deliver over 100 tons of cargo to the Moon, far more than any rocket in history. For Mars, it means the difference between a one-way experiment and a sustainable colony. Orbital refueling also enables reusability on a truly interplanetary scale. A Starship could leave Earth, land on Mars, refuel using locally produced methane and oxygen, and return home, all without wasting its hardware. It's the foundation for a circular, living system of transportation across the solar system. Beyond exploration, this technology could spark entire new industries. Fuel depots in orbit, commercial tankers operated by private companies, mining operations on asteroids supplying raw materials for propellant, even power stations converting solar energy into storable fuel for interplanetary trade. In essence, refueling in orbit unlocks the possibility of a space economy, not just missions, but markets. But every revolution carries risk. SpaceX's plan is ambitious, perhaps audacious. Orbital refueling requires near-perfect synchronization, cutting-edge automation, and cryogenic management far beyond anything achieved before. There are also competitors. Blue Origin, ULA, and NASA all explore versions of in-space refueling, each approaching the problem differently. Some envision depots built in lunar orbit, others automated systems that connect to multiple spacecraft at once. But none have yet demonstrated the full process on the scale SpaceX intends. Then there's the human factor. Can we trust robotic refueling hundreds of kilometers above Earth? Can we maintain it, regulate it, and keep it safe? And what happens if it fails during a mission to Mars, halfway to another world, with no return possible? These are not just engineering questions. They are ethical ones. They challenge our very concept of risk, responsibility, and the cost of exploration. But SpaceX has built its reputation on embracing the impossible, turning audacity into achievement. Falcon 9 was once a dream. Reusable rockets were once dismissed as fantasy. Now they land, routinely, every week. Perhaps orbital refueling will follow the same path, from skepticism to inevitability. Every great leap in human progress has come from learning how to harness energy more effectively. Fire gave us civilization. Oil gave us industry. Electricity gave us power. Now, the ability to store and transfer energy in space may give us the stars. Orbital refueling is more than a technical milestone. It's a philosophical one. It marks the moment when we stop treating space as an obstacle and start treating it as an environment. It transforms spaceflight from a series of isolated missions into a continuous journey, one that could last centuries. When future generations look back, they may see this moment. Not the first moon landing, not the first Mars colony, but the first time humanity learned to refuel among the stars, as the true beginning of our interplanetary civilization. Because once you can refuel in space, the solar system becomes your highway. Every planet, every moon, every asteroid becomes reachable. Every destination becomes possible. And when a refueled starship burns its engines above the blue curve of Earth, streaking toward the infinite dark, it will carry more than methane and oxygen. It will carry the one thing that has always fueled human exploration: hope.